Everyone, we are back and we are going to do our Pset 6 solution videos. So here we're looking at 2D grain growth. So we should remember that we have a function, average grain size squares versus my average or not, squared value is proportional to some constant m times t. So our average grain size scales with t to the 1/2 value. And this m has a component in here that's basically 1 over t times some exponential minus some delta g over kt. So let's look at the actual problems telling us to do. We see that these curves have kind of this kind of power law scaling. It's t to the 1/2. And we see that the values, the slopes, increase as a function of temperature. And that's predicted by this basically variable m here in this equation. So that's why the scope, basically we should expect them to increase as time increases to the 1/2 power. That's our scaling law. Why does the grain size or this increase temperature? Because this m value, and elaborate and point to the specific variables. Well, there it is there. So that's it. So that's problem one, basically down the drain. So there we go. Number two. How can we determine for 2D grains which ones will grow or shrink? That is the von Neumann principle. So if n is greater than 6, dr bar dt will be greater than 0. N is less than 6, the number of neighbors that the grain is touching, dr bar dt is less than 0. If n is equal to 6, dr bar dt will be equal to 0. So that's effectively what we're going to be looking at and doing in here. What's the criteria for 3D particles? So remember we said that if A is greater than A bar, then my dA dt will be greater than 0. If A is less than A bar, dA dt is going to be less than 0. And if A is equal to A bar, then dA dt is equal to 0. So let's zoom out a little bit here. Excellent. So if I have a particle with high curvature and a particle with lower curvature, where will the atoms move? So we can see this kind of here. So if I have a large particle and a small particle here, the flux of atoms is proportional to your chemical potential, which is proportional to your curvature, which is 1 over r. So if I have a smaller radii, let's label this 1, let's label this 2. So here, my chemical potential of 1 is much greater than my chemical potential of 2 because the radius is larger. So I'm going to flow from high chemical potential to low chemical potential. So from 1 to 2, ease your energy here, then here, and that's where they're going to move. Excellent. That's number 2. Really nice. So I'm nucleating a solid particle from a liquid solution. It is contained in a container with solid copper walls that have no special coating, meaning the particles can solidify on the walls. So I have a system where we're talking about here is I have here, and my particles can solidify on and at these walls here. What are the 2 free energy terms of this scenario? So this is heterogeneous nucleation, but in general, my delta G homogeneous is going to be equal to basically minus 4/3 pi r cubed times delta GV plus 4 pi r squared gamma SL. And my delta G homo, or hetero, is going to be equal to delta G homo times basically a variable s theta that's related to kind of the geometry of my system. So I'm going to look at and open up Mathematica because I want to start to plug in those values effectively, or those general terms in the equation, because it'll be helpful a little bit later on. So what pushes the particle to become solid? So we want to nucleate if do this volume term here. So let's go ahead. So delta G homo is equal to, let's just call it volume. Volume of my sphere is equal to basically 4/3 times pi times r cubed. There we go. My area of my sphere is going to be equal to 4 times pi times r squared. And then my delta G homo is going to be minus volume of the sphere times del GV. And our del GV is going to be equal to del H times del T divided by Tm here, plus area of my sphere times gamma S. So this term here, my del G hetero is going to be equal to del G homo times S theta. It's going to be a function of some variables here. Excellent. So now let's go back to OneNote. And All right, so which of these is going to push towards nucleating a solid? So to nucleate a particle, this is going to be my negative free energy term, my volume term. That's going to want me to be a solid. This, the energy penalty I have to pay is surface area. That's going to make me become a liquid. So that's effectively what's going to happen. What happens when undercooling increases? Is the particle more or less likely to become a solid? So we saw that delta GeV term is equal to delta H of fusion times delta T, which is my degree of basically undercooling or supercooling. So as my undercooling increases, i.e. as my temperature becomes colder, I'm going to want to become a solid because I want to be solid at cold temperatures. Excellent. So below is a plot of the free energy of the system as a function of particle radius size. Draw the same curve and also integrate. So where are our curves going to grow or shrink? So if I go from here to here, I'm increasing my energy. Particles aren't going to want to grow. They're going to want to shrink here. And they're going to want to grow over on this side. So this is my original system, my heterogeneous system. So now we want to draw the same curve, but a system where the coating is special, prevents particles from attaching. So that's our heterogeneous system. So my heterogeneous is going to have the exact same particle critical radii here. So right at the same maximum, this is our RC, where our basically derivative is going to be equal to 0. And it is going to be higher. Why? Because if I attach the walls, like here, versus if I just nucleate a solid here, I'm creating less surface area in this system. So I'm paying less of an energy penalty, so it's easier to essentially nucleate, as we've talked about in class before. Draw another curve for the system, but an increase in undercooling. So if I increase my undercooling, let's go back to the system here, and actually it'll be very convenient for us right now. So if I want to find that maximum, I'm going to solve derivative of del G homogeneous, set this with respect to R, excuse me, and set equal to 0 and solve for R. So here we can see that critical radii. I could do the same thing here, del G hetero. I have the same radii. The only thing that changes here, and actually I could plug that in if I want to find the energy. So I could do, for example, del G homo slash dot R, actually just do slash dot this, and I could do the same thing here, but then change to hetero. So what's the energy of my system at that maximum value? Del G hetero, this, and the only thing is this S theta will be less than 1. So you can see here that shrinks essentially that maximum here. But my critical radii is inversely proportional to my amount of undercooling here, del T. So if I increase my undercooling, there's got to be a better way to transition back and forth. My curve is going to shift from my original system, is going to shift kind of like over here. So it's going to shift to the left. If I decrease my undercooling, it is going to shift over here to the right. There we go. So the steady state nucleation rate for the system with no particle adhesion is shown below. So no particle adhesion is on here. Draw the curve for the system with particle adhesion. So with particle adhesion, it's going to be easier. I don't need as much, basically undercooling here. So it's going to occur. I need less undercooling to kind of get this system started. Again, high undercooling, that's where nucleation dominates. Low undercooling, that's where growth dominates. And then driving section for critical radii, already solved it. Energy, already solved it. We're done. So thank you very much. I'll see you in the next video for the next Pset. All right.